Hi guys, welcome back to my YouTube channel, and today we'll be going through proof by contradiction. Like I said in my last video, you need to know a couple of standard proofs and also the general idea of how to do proof by contradiction. So first of all, if I go through what proof by contradiction is just when you want to prove something by proving that the opposite is impossible. So whenever you do proof by contradiction, there's a few steps you need to do. So the first thing is just that like normally given in the question. So that's stating what you want to prove. So for example, this would be like the question saying prove there are an infinite number of primes. Like that would be like the first part. Step 2 is assuming the opposite. Now this is really important because people get this wrong a lot. So assuming the opposite, this is also called a negation. So if you're proving something is even, the negation would be it's odd. If you're proving something is positive, the negation would be negative. If you're proving something's rational, the negation would be irrational. So the step 3 is actually proving, like showing that there's a contradiction with the opposite. So this is what I said, where you want to prove that the opposite is impossible. So you have to derive a contradiction from somewhere. Like you have to do algebra, some manipulation, completing the square, things like that. And then step 4 is a conclusion, which you always need. So this will be like, this is generic. You always write this at the end of a contradiction. You'd write, this is a contradiction. Therefore, our assumption was false. And the original statement is proved. So that's like the basics of how you do proof by contradiction. So we can go through, there's a few standard ones that you need to know. I think there's 8 that you need to know that can come up that you can just memorize, but they could also ask you some other ones that you just have to figure out in the moment if it comes up in your exam. But you should definitely know the standard ones. The first few are quite easy, so we'll do a few in this video and we'll do the rest in the next video. So proof number 1, this is there is no greatest integer. So obviously we know that the number line, if we draw a number line, it will go on for infinity, like it doesn't stop. So we need to prove this. So the way you prove this by contradiction, first we have our assumption. So we can say, assume that, well, obviously if there is no greatest integer, the opposite of that would be that there is a positive integer, or there is a integer that exists that is the greatest number. So you can say, assume that there is a greatest integer, and let's just call that n. So we're saying there is a greatest integer. So how do you prove that this isn't the biggest number? Well, we can just simply say, consider n plus 1. So if we consider n plus 1, and we said that n is our greatest integer, we can say, since n is an integer, that means that n plus 1 is also an integer, because if you add 2 integers together, you'll obviously get an integer. Furthermore, the main part of this is that n plus 1 is greater than n. And here you can see we have a contradiction Because if n plus 1 is more than n, and we said that n is our greatest integer, then the two of those can't be true at the same time. So we've done, this was our step 2, our assumption. This part is our step 3. And then step 4 is just our contradiction, which you would just write, I can write this again. This contradicts the assumption that n is the greatest integer because n plus 1 is a larger integer, and we've just shown that. So then you'd write, therefore our assumption is false and there is no greatest integer. So that's it. That's how you do proof by contradiction. Okay, so that's the first one. It's really simple. Like, you could do like, there's various, like, you could say, instead of this step, you could do loads of things. You could say 2n, because that's also an integer and that's bigger than n. You don't even have to add 1. You could add any positive number and this would work. So yeah, that is our first proof. We can move on to our second proof. The second proof is a bit more tricky to understand. So proof number 2. Prove there are an infinite number of primes. Like, this isn't as obvious because when you think of prime numbers, obviously there is no pattern to prime numbers. There's no sequence. So this is a bit harder to prove because we don't know this as a fact. Like, obviously infinity means that there will be an infinite number of primes, but over here we can see integers. We know that it's quite logical to see that there's a greatest integer, or that there are no greatest integers. So for this one, the first thing we assume is the negation. So we would assume that there are only finitely many primes. So I would say P1 is a prime, P2 is a prime, P3, all the way to, let's say, Pn, where n is the last prime. So now this is a bit tricky to see, but I'll explain. I'm gonna let x, a number, be equal to the product of all these primes. So I'm assuming that there are a finite number of primes and x is these primes all multiplied together. So I'm going to call this the product of all primes. Okay, so if this is the product of all primes, this means there are no more primes we can possibly have. Now I'm going to introduce another number, y. Okay, y, I'm going to let y equal to x plus 1. So this means I've introduced another number that is one more than the product of all the primes. So what does that mean? Well, if all of these numbers are primes, we can say that when y is divided by any prime, p of n, like any of these primes, the remainder has to be 1. So it doesn't matter which prime we pick, because it's one more than our x, any prime, when it's divided by, will also always have a remainder of 1. So let's have 11 is a number, or let's say I had 2 primes. What are 2 primes? 2 is a prime. Its factors are 2 and 1. 5 is a prime factor at 5 and 1. So let's say you times these together, it's 10. So 10 plus 1 is 11. So now 11 we divide by 5, we get a remainder of 1. 11 we divide by 2, we get a remainder of 5. So this is true, this is fine. But that means that if y is 1 more than x and it has a remainder of 1, then y doesn't have any prime factors from our list because it's not divisible. So let me just write that down. Therefore, y has no prime factors from our list because obviously they don't divide fully, they leave a remainder of 1. So this could mean, if they don't divide fully, that y is a prime. Or there's also another possibility that it has a prime factor, but it's not in the list. So we can say or has a prime factor, not in our list. Either way, if we've said there are a finite number of primes, then and y is a prime or there's a prime not in our list, either way means we have another prime. And this is a contradiction because we said these are all of our primes. So then we can say as a statement, either way, there exists a prime not in our complete list, which is a contradiction. Then we can just write our concluding statement. Therefore, the assumption that there are finitely many primes is false. So there are infinitely many primes. And yeah, that is it. So that is the basics of proof by contradiction and the first two standard proofs that you need to know. So the first one, simple to understand. The second one, a bit more tricky, but once you if you memorize it and you get your head around it, then it will make sense. But those are two. We'll have 6 more left. I'll do those in the next video. We need to prove that if n squared is even, n is even. We need to prove things about rationality of numbers. There's also proving there's no integer solutions, proving multiples. So there's quite a lot of things, but we'll get through them. And yeah, that was it for today. I would really appreciate if you like and subscribe, and I'll see you guys in the next video. Bye.